Recording in progress.
Okay. And the sound is okay, Nathan? We already asked that several times, didn't we? Yeah. So now I'm going to share the screen, but those who are online may want to keep an eye on the camera as well. I have a few visual aids. Now, if I can only find
Did it help?
share screen first, whole screen, share. Okay. All right. So the title of this, and well, you might notice that I look a little bit different from the listed authors, all three of them. I've got a team of 4 students, undergraduates, who are working with me on these altitude balloon flights. 3 of them are biology majors, really pre-med, and then I've got 1 physics major who just came on this fall, this spring. So my pre-med students sort of got cold feet at the last minute with presenting in front of an astronomy meeting, but I decided, okay, I'll be happy to give their talk then. So I'm actually giving it a little bit different from their listed talk, just because I've been presenting a few different aspects, but I'll give you an overview. So this is our high altitude research projects series of missions, which is being run between me in natural sciences and Jim Bruneau over in our business department. He's actually a professor of business information systems, but he's got a physics background, does a lot of computer programming and even like external consulting work, and builds his own electronics and has his own ham radio license and such. So he's been great for this. That's Jim there in the overalls as we were building our first test article. You can see the triangular basswood frame that we're mounting this stuff to. This is our helium filling test. And you can see all of the team there, or most of them. We've got actually 1 more biologist now from that. So this is just to make sure we knew how to get the thing up off the ground. We've got a helium balloon. This is, in fact, the actual one that we tested in this one here. We're not going to use it for flight because, you know, now that we stretched it out once, we don't want to risk the whole mission on it. There's a parachute down below that, after about 20 feet of kite string underneath it. And then we've got the parachute. This is not the one we flew. This is another one we've got. This is much larger. And the parachute's actually a structural part of the whole flight line going down. So we tie on the string to the top here, the parachute that holds these risers in place, and we're not going to wind up using this little cardboard frame for that there, but we'll be building our own. And then we got another 20 to 40 feet of string down below it with the payload. And for tracking, we're using several different devices. This is a GPS system here. Spot Trace is the brand and model. And it's a GPS receiver that then uplinks, downlinks your coordinates to a satellite that then puts it onto the web. And so as long as that thing is facing upwards and you're below 60,000 feet, you can track it then live every 2.5 minutes, I believe. It updates the locations. It's fantastic, but it doesn't work above 60,000 feet. GPS is required to be, it won't operate, commercial units won't operate if they are both above 60,000 feet and moving faster than 1,000 knots. Now, we're not moving faster than 1,000 knots with a balloon, so we should be able to, the GPS should work fine, but most commercial manufacturers kind of chicken out with the requirements, and they say, let's not bother with having the dual test. We'll just say if it's above 60,000, we shut off. So in that case, we've got this, which is another GPS unit that works at all altitudes and up to 1,000 knots. And it then rebroadcasts on 2-meter ham radio wavelengths, which then come back down to the ground through a network of amateur radio stations, repeaters, that store the signal and repeat it automatically bouncing around the country until it reaches an internet gateway, at which point it maps it out on the web. And it sends out not just the GPS coordinates, but it's a 200 or so bytes of data, ASCII data. So you can put text, you can put numbers. We've got temperature, pressure, altitude, speed, battery voltage, as well as the coordinates. And now we're working on doing this with 2 ways. So that's APRS, Automatic Packet Relay System. And we also have, for the last bit, because sometimes those won't work when they're right on the ground then, we have just a plain old radio beacon. And then we take this portable homemade Yagi antenna, hook it up to our handheld transceivers with our ham radio licenses, and we just scan around until we get a strong signal. And that's what this Fox is here, like in a fox hunt. It's sending out a beacon. You can pre-program it with your call sign, and with a little musical tone, it'll broadcast, and you just home in on it. In the end, we never actually wound up needing to use the Fox. So the biologists, here's Katie Durbin. She's our graduating senior in the lab there. They've been collecting tardigrades, which we're using land-dwelling ones, which live on moss and lichen. And they've been collecting them around campus and off into Shawnee State Forest. It's about a day or 2-day process to screen them out and to separate them. And then, there we go. That's under the microscope. That's really only about a magnification of 40 times.
Sorry.
All right, that's me asking you what am I looking at here. But you can see the fine grid graph paper on the background for scale. That's a usual.
That is a tiny drop
very
of
fine
color to get
green,
to that. What'd you call it
grid.
again? A micro?
And it's actually not that tiny. You can just barely make it out with the naked
Oh,
eye.
diameter of that
But
ball?
it looks like a speck. But this is a fairly large one, and it takes so long to do them that we're now switching over to using some that Marshall University gave us a flask of. We would get like 1 to 4 for a whole flight. We've flown at most 3, and we flew one flight with 1. So the statistics are not great to look at their survivability. And these animals are able to survive freezing. They have been taken down to millikelvin and thawed back out and scampered off and were fine. They have been subjected to strong radiation. They survive that. They've got a damage suppressor protein that actually repairs their DNA. Fantastic stuff. They can survive lack of oxygen. They can be in a vacuum. They can be in strong salt content and dried out. That's actually how you can ship them. You just dry them out, and then you put water back in, and then up they go. So these are fantastic creatures. They've actually been put into low Earth orbit and brought back, exposed to space, brought back, and most of them survived and even laid eggs, and the next generation went off. So this is why we're interested in trying them out at high altitudes to see, all right, if they've been taken into space, what about putting them up into the stratosphere? Can we do this on the cheap? So these whole flights cost us a lot less than a space mission. This cost us several $100s for all the equipment, maybe $1,000 for the whole thing. But if we recover it, then we only have to replace the balloon, which is about $80 for this one, and the helium, which is about $2 a cubic foot. So we've got these online tools that allow us to do the performance calculations for the balloon. And then we can put in a flight prediction based on the high altitude wind models. This is the SONDE hub, SONDE hub, predict.sondhub.org, as in radiosonde for weather balloon. And so it was predicting if we launched from Aberdeen, Ohio, right off across from Maysville, Kentucky, that it was going to go off like that. You see the little explosion symbol, that's where it would burst. After all, the balloon inflates to about 5 feet in diameter when we put in 100 cubic feet of helium. But when it goes up to its maximum altitude, it stretches out to 4 times that diameter. It hits the breaking point of the latex, it bursts, and that's actually what we want to happen because that's how we recover the payload. Okay, so that was going to bring it down. This was fantastic. 8 miles away, very close by. Normally, when you're in the summertime and the jet stream is stronger, then you're having to chase it off for about 100 miles in a straight line to the east, which is all covered in forest. Oops. We don't want to bring it down in the woods. So we're looking for central to western Ohio, northern Ohio, or Indiana, which is vast treeless plains there. It's the easiest place for us to bring it from. Unfortunately, I didn't put enough helium in and show flight video. Allow me to show the flight video. This is
Sure,
a
video.
condensed version. Yeah.
This is our big old balloon.
Okay. You can see Maisel in the background there, off just in Aberdeen City Park.
Crazy, dude.
That's Corinne Woods, our videographer and biology major, who is, doing a fantastic job with it.
This is
There's a
crazy.
payload on the ground, the balloon there,
Should we
you see the
Down, down,
parachute
down
in the
for
middle,
like 3 or something.
which also has the long antenna for the 2-meter transmitter. 6, 5, 3, 2. Now the onboard camera.
No way.
And I didn't secure the transmitter very well to the parachute, but it's fine now. And I got stuff in the line I was using to keep it on the ground from the
Let's take a try.
winds.
Bird. Wait.
All right, got it. Up it goes. Fantastic. And down into the.
Oh.
Okay, well, use drops of water, but otherwise, okay.
You're like, dang, why we moving?
I think it's fantastic on this video there. But now the trouble is,
Oh my God. What if it doesn't climb?
it's not really going sideways. We weren't sure we were gonna clear the steeple on the church there.
Oh shit.
Yeah.
Wait.
And now down. Connected to the but it did go up. The camera was cut out after this point here. We got it to 87,000 feet. This is 83,000 after we passed an airliner at 40, at 30. You can see the curvature of the earth.
Yeah.
You can see the black sky.
Yeah.
This is the Ohio River.
Oh.
There's
yeah.
the Cincinnati Airport.
Oh,
There's
okay.
downtown Cincinnati, right there.
That's NKU at the bottom there, yeah. Coming up, yeah. That's very cool.
This, by the way, the twisting is very, very common. Actually, trying to keep it from twisting is something we like to do. Here's looking up north, and you can see how treeless and flat that is,
Yeah.
looking up into the Midwest. Now, this is neat. This is Chillicothe, Ohio.
Uh-huh.
This is the Scioto River Valley,
Yeah.
Waverly, Ohio. This is a dry valley. And if I hold it there very quickly at the end, there. Okay, here, this is my pointer. Well, this is the pointer. All right. This is where the glaciers came down to, right to there. This edge with the dark trees, that's the Appalachian Plateau, the foothills. And that's what stopped the glaciers.
Uh-huh.
This river, this is the Ohio River. Okay, look at this is the corner now. This is the Ohio River. Here's Huntington here. Here's Portsmouth on the Ohio River, and then going on up towards Cincinnati down there. This was originally flowing northward and eventually connected over to the Mississippi. What's this section of the Ohio, which was called by the geologists the Taze River, like the Taze Valley out towards Charleston and Huntington, flowed up north here, joined the prehistoric Scioto River, came up together, but when the glaciers came down, they blocked it, made an ice dam. This turned into a lake with a volume equal to the Great Lakes today. We were under 900 feet of water here about a few 100,000 years ago. Eventually, it lifted the ice dam down here, escaped down, and then it eroded a cut here, which is where we're sitting right this moment. It eroded through this ridge, cut through, and if you look when you go home, look on 23, those cliffs there, that's from the erosion of a fairly quick event over, some number of years maybe. And it flooded through, cut through. This became a dry valley. There is no river here now. This is a prehistoric river valley.
Oh.
And you can see all of this from that there. It's a fantastic little tool. Yeah. Okay, so that's our flight there. We passed one airliner at about 30,000 feet or so, like that, about 1 mile away from it. We can make out some details. We actually don't have to file a flight plan because we are so lightweight, we fall under the unrestricted category, or at least these are the restrictions. And the kite string is designed to break if there's more than 50 pounds of force that hits it, So if we get hit by an airliner wing, it just goes snap and all it goes and the plane's fine. So what it actually did was it almost went up to Cincinnati because I underfilled the helium and it didn't rise quickly enough. And it came on down in this field here. I'm tracking on the GPS. Jim is in the car and I'm giving him directions. Go to the left, there's a silo 200 yards past that. The farmer was out in the field and said, oh yeah, it's your balloon. It's right down over there. Go ahead and you're fine.
At least you were not in Texas, that's short, right?
Our second flight, we launched from here because there was a high school science camp that wanted to be part of it. But the trouble is that takes us into West Virginia, which is all trees. But we decided we'd try to put enough helium so it would go up, burst quickly and come right down, right on the edge there. Maybe it wouldn't be stuck up in a tree. Again, underfilled it. And so where it actually went was much, much farther, all the way up to near Clarksburg, West Virginia, not too far south of Morgantown. We were getting pinged off of places, stations up near Toledo, other times down near Louisiana. High altitude winds, it's the doldrums, and right now, there it is in that tree. On the edge of Tyler County, it is 80 feet up. I cannot get it, I can't see it. We know where it is to within 30 feet. We got up there, and this is the county road that leads up there. This is County Road 55-2. That is a creek. I mean, it's not like a creek, it is an actual creek, but it's a designated county road.
Oh, did you drive on that? No.
Yep. Yep. Luckily, I had Christina's Subaru Forester, which had enough clearance that I could get over it. I could not have made this. This actually looks easier than it is. This is on the way back down. On the way up, you can see the big rocks are going over there.
The forest I can drive.
And at other times you're going through, this is the road still. Okay. And so, and I won't give you the whole travel log, but okay, there were interesting places. That's where it is. It's in one of those trees in that picture. And this is, okay, well, this is not my reaction. This is me about to start a little video thing then to explain to the kids back home at the science camp why we didn't recover their experiment.
Okay,
Okay, the equipment to recover it, by the way,
so let's take a look. At
includes a bow and arrow.
One thing you want to bring to
Where
you on
the-
the tracking and recovery mission
was-
is a very good map.
You see my
This
fishing rod.
Atlas and Gadget here by Bowen is really the best one that I know
Right.
of. It has just about, I think, really every
Now you've got a
single
loop
back
around the
road,
frame
even
pulled out
down
of
to
the tree.
dirt tracks,
That
and
works
in
if
some
you can
cases
see
which
it.
are
Yes.
not
It
even
also
not
works
even
better if
dirt
you're a good
tracks,
shot.
but just
All three of my biomedical students said that they were good
Is the,
shots,
uh,
but none of them came with me the second time. Okay, but anyway, so we got the APRS data. We do a little work with the software, altitude, battery voltage, temperature, pressure versus altitude comes up very nicely, except for some weird glitchy data. Pressure versus time, horizontal speed, temperature. We hit, this is in degrees Fahrenheit there. We got down on the way up to minus 28 degrees Fahrenheit, and then it warmed back up to the thawing point, at which point it burst. That seems suspicious to me that it hit exactly 32 degrees Fahrenheit and then burst. But on the way down, it was much colder, maybe because of the lack of the balloon re-radiating heat out, not really sure. It hit minus 48 degrees Fahrenheit. Pressure and so on. Anyway, but we get lots of data. It's fantastic, a fantastic resource. We killed all three tardigrades, sadly. Neil, Buzz, and John Glenn were the three names. And the second flight, we don't know because we couldn't recover the tardigrade, much less anything else. So what we're doing now is we're building a new system. We're going to be using some styrofoam to put the equipment in, and hopefully we'll be a little more, not aerodynamic, but tree branch dynamic, where we can sculpt a nose cone onto it. Then if it gets stuck in a tree, we tested out using nichrome wire to burn through the kite string and let it drop out. So if we're stuck on that, then we just cut the cords and hopefully it will come out then. And if that doesn't work, we take a bow and arrow again, put put a blunt ball on the end of it and try to shove it out of the tree. That's also a recommended procedure. So I'll end there, and we do hope to be getting some, we got cosmic ray data. We just took a video camera, cheap $60 video camera, wrapped the lens in electrical tape, set it to record video, and then just looked for the flashes. And once we got to 10,000 feet, we started seeing them. Actually, I should put that up here. I had way too much. Oh, here we go. There's our first cosmic ray right there. And this is integrated over 10 minutes at 80,000 feet. The background is a little uneven, but you can see the streaks and all. Low energy cosmic rays are probably what are making horizontal streaks in the curves and such there. High energy are punching straight through. And it's a very easy experiment. It was a $60 cosmic ray detector.
Wow.
And there's the intensity versus altitude. So I'm already a little bit over time, but I'll take any brief questions people have. Yeah.
What did you do to kill the tardigrades?
We don't know yet. We put them in 180 degrees Celsius freezer, they're fine. We put them in a vacuum chamber, they're fine. We don't know why doing both simultaneously did them in, except unless it was both simultaneous. So we're doing more lab work with them, but we're also looking at the biomedical students would like to do some actual biomedical work with them. So we're now getting, we're cloning the DNA sequence that produces the damage suppressor protein. And we're going to clone that into E. coli bacteria so that they will make it. One will test to see if that gives the E. coli radiation protection. Other teams have done this with human cells in a petri dish, not like growing mutants or anything. And it did confer some radiation protection. So we're asking them if they can send us some of their cell lines or their plasmids, which are little DNA loops that you then use in the cloning. So we're working with that. We're working with the team over at Marshall. They gave us a flask of 5,000 tardigrades. They said, here, why don't you just use this as a starter kit, rather than us gathering 1 to 4 at a time. But Marshall would like to see which ones we were using because ours are kind of robust, apparently, well, except in flight. But now an Italian team we contacted asked if they could fly their genetically modified tobacco pollen, because it's used in a lot of plant genetics. And they put the damage suppressor gene in that, gotten the pollen out of it, and they've been wanting to test it in a space environment. So they're asking if we might be able to fly that. So we may be doing professional biomedical research with our little cheap, $700 balloon kit that we're putting together.
So, how can you make sure that next time you have the right amount of helium in your balloon?
I have been talking with people who have got 100% success rate with dozens and maybe 100 flights on how to do that. And we'll just have to we've got our ballast tank, just a jug of water with the right weight equal to the lift we want up. We'll have to disconnect it from the helium when we think we're about right, tie it on and see if it's about right. Then if we need more, then we reconnect it. I was trying to do it with the hose still connected.
Yeah.
And it was raising the ballast, but you get the stiffness of the hose as part of the problem. And we're also going to put a cut down line from the balloon. So if we start to drift over an area that is going to be, the winds are pushing us towards more woods, the software should allow us to predict the landing point based on the profile going up in the air. It knows on the way down, it integrates the wind speeds and all. And if we get to where we're getting close to the edge of that, we cut the line to the balloon and we come down early before we wait for the balloon.
So you have the payload coming down, the balloon goes into space
and it goes pop.
And so
Once it hits, at most 120,000 feet, it'll burst. Yeah.
Have you tried looking for your balloon in the winter? There are no leaves on the trees.
Have we tried looking for the balloon?
yes,
In the winter.
Oh, no, have not. We know where it is. The thing is, it's
But on which tree?
which of the trees within the space the size of this room, we know where it is.
Yeah.
We can hire tree climbers, $50 or something like that, to go up and, shove it out or cut a limb of whatever. But we don't know which of those trees. So,
Right.
but yeah,
Yeah.
the winter,
Yeah.
that bright red balloon. But honestly, we need to get just a drone, get up there, get
Yes.
eyes on it from above.
Sure.
Now we know which tree.
Yeah.
So that would be a nice little internal grant of $1,000 or whatever to get a little mini drone, or less than that even.
less than that.
Yeah. So That's it. Hopefully we'll build into getting little lightweight telescopes on there too. Any questions online?
I don't see any comment.
Okay, that won't keep us too far off. So our next contestant is,
Nathan.
okay, so we're gonna set this up for online, so I'm gonna stop sharing.
Online, you can, oh, you need to stop the sharing.
Yes.
And go to the top there, go just to the top of the red button on the top. Stop sharing and you're good. Nathan is good to go.
All
All
right,
right,
Put
sounds
this
good.
on mute for now.
There we go, and I have to swap this.
Now it's working.
Okay, great. All right, well, I'll go ahead and get started then. Hello, from the great state of Kentucky. I'm going to tell you a little bit about a program that I've been working on off and on since 2008. I originally discovered the problem as part of my thesis work, and I'm glad to say that we finally have a paper out that seeks to solve the problem. So I'm going to talk a little bit about RRLFE. It's a new method for determining RR Lyra star metallicities. So just as a reminder, RR Lyra stars are intrinsically pulsating variable stars that have a visual amplitude between about 0.2 and 2 magnitudes. And they all have periods of less than a day. And so they're, horizontal branch stars. And they're located in the instability strip. There are sort of two types of RR Lyras that I'm going to focus on. There's the RRAB, which have these sort of sawtooth shape to them and have, relatively large amplitudes. And there is RRC stars, which are more sinusoidal. The RRABs pulsate in the fundamental mode, and the RRCs pulsate in the first overtone. So why do we care about RR Lyra stars? Well, they're old. They're all greater than about 10 gigayears. As a result, because they're on the horizontal branch, they're burning helium in the core to produce carbon through the triple alpha process. They're radially pulsating. And the thing that they're used for is that they're very good standard candles. And this allows us to use them to measure distances throughout the galaxy. They're very easy to identify because of their, distinct light curve shape. And they have, of course, an absolute magnitude of about 0.6 mags in V. And by looking at RR Lyra, we can not only trace out structures in the Milky Way or other nearby galaxies, but they also tell us about the environment, in those parts of the galaxies, back 10 gigayears ago, right? They, on some level, they're both little time capsules and little lighthouses to let us understand what's going on there. And so, things you can explore and things I've looked at are galactic disk structure and halo structure. So, to use an RR Lyra as a standard candle, I said that they all have absolute magnitudes of about 0.6 in V, but that about is a bit of an issue, right? Because we want to get good distances. And there's a relationship between the absolute magnitude and the metallicity of the RR Lyras. And so there's different ways you can get metallicities. One of the most direct ways is just to do a spectroscopic observation of the RR Lyra. You can do that using high resolution spectroscopy and just look at the iron lines directly, or you can use low resolution spectroscopy and look for elements that are correlated with the iron to hydrogen ratio. So, we have all of these different surveys that are giving us RR Lyras, right? So we're just finding them all over the place, right? So these are all photometric surveys. But we need some way of following up these stars to get their metallicities, right? To be able to use them as proper standard candles. So I think this is where low resolution spectroscopy can help, right? We need a way to easily do, quick spectroscopy. And the benefit of low resolution is, right, it requires relatively low signal to noise. So it means it can be used on dim stars, or you can use small telescopes on bright stars. And so what we wanted to do was produce not only a calibration, but an actual software package that you could feed your spectra into, and it would produce metallicities in a consistent way. So how are we going to do this? Well, the problem with RLIRA in general, when you're trying to do spectroscopy of them, is that they pulsate, and as a result, they change temperature through the pulsation. So you see these three spectra here. These are all of the same star, right? But you notice that the lines look very, very different. And it's because the star is at different points in its pulsation phase, and it has different temperatures. So what we can do is we can use the hydrogen bomber lines. So we have the beta, gamma, and delta lines marked here to get a temperature. And we can use the calcium 2K line as a measure of metallicity, because calcium 2 is going to track the iron to some extent. And the calcium 2 line, or the bomber lines, are a function of temperature only for the most part. And the calcium 2 line is a function of both temperature and metallicity, but if we know the temperature, then we just get the metallicity, is the idea. So how do we analyze these lines? Well, in the past, of course, you could measure the spectroscopic type, right? So if you look back in the papers from the 50s and 60s, that's oftentimes what they refer to. But in our case, we're going to use equivalent widths, where we literally fit the line, and then we talk about how wide the area under the line is if it went from 0 all the way up to the continuum. And so when I say the equivalent width, that's what I mean. So this gray blue area and this blue area are the same area. And so by talking about the width, we're effectively, that's another way of talking about the area under the absorption line, or within the absorption line. Okay, so we're not the first people to think of doing this. There was original work on the delta S method, done back in the 50s and onward, where they're looking more at changes in spectral type. In 1994, Andy Layden used an equivalent width method, where again, he looked at the calcium K line and the bomber lines. The problem with the delta S method is that you really have to be near the pulsational minimum for it to work relatively well. You run into problems if you get too far away from that. With the equivalent width methods, we were able to get a little bit farther away, right? And so that made it a little more useful. In fact, that's the standard method that's been used, since '94. And so here's an example of several RLIRA stars measured at different points in their pulsation sequence. And you can see that in a plot of the width of the calcium K line with respect to the equivalent width of the hydrogen lines, that there is something like a plane, you can almost think, cutting through this plot. Whereas you change the metallicity, so we got minus 2.4 Fe on H down here, all the way up to minus 0.43 Fe on H. For constant metallicity, you have these straight lines that cut through this plot. And so that's what you try to use to convert equivalent widths into a metallicity. Okay. So the problem I encountered when I tried to use this method is that it really was only designed for RR type AB stars, which are cooler stars, cooler than RRC. And so when I started plotting up the Layden method versus when we were getting Fe on H by doing sort of by hand calculations, we discovered that as we got to larger widths, equivalent widths of the bottom line, so higher temperatures, that there was clearly a linear slope that was starting to appear, right? That should not be there, right? These stars were not more metal rich or something like that than these stars, right? What was happening is that the method had a asymptote in it, right? That once you started getting too far away, you start extrapolating from where it was designed to work in, you would start to get this linear term that appeared, and that of course is not very useful. So we're like, well, what can we do to try to fix this? So we decided to include both AB and RRC stars in our sample, and we decided to start using Monte Carlo methods to fit the equivalent width. So what we do is we use a standard piece of software that I'll talk about more in just a few moments to fit the lines. We then adjust the flux in each pixel by its Poisson noise, fit the continuum, fit Gaussians to each of the lines, and then convert those into equivalent widths. And we do that several times, take the average standard deviation to get a final value and error. And then the goal is to then take these low resolution spectroscopy and connect it to high resolution spectroscopy of the same stars, be able to find what the transformation is between the two sets. So here is just an example of some of the data that we took at the McDonald Observatory. So this is low resolution, right? It's about R1000, and it covers, sort of the visible range. And so we collected 19 RL Lyra stars in this way. And so here's an example again of the same star going through its pulsations. Okay, so here are our 19 program stars. The black dots are photometry taken of those stars through various sources. We pulled photometry from the TESS satellite, from AAVSO, from KELT, etc. We then fit a spline to the phased data, and then the blue lines are our spectroscopic observations. And so the goal was to figure out what the phase was of when each spectra was taken, right? The photometry and the spectra were not taken at the same time, although the photometry usually spanned the time that the spectra were taken. And so
5 minutes.
Sorry?
5 minutes.
Okay, thank you. And so we use this photometry to actually assign phases to our spectra to make sure that we could actually use our method in a wide variety of phases. And so here's all the RABs in our sample. Here are all the RCs. And you can see that we cover a lot of different phases when we're doing this. Okay, so, if you have a high resolution spectra, right, and you want to fit your lines, right, usually you use a volt profile. And you can see that the wings are pretty wide on these things. The problem is that when we started to do that, we discovered that it was relatively unstable, and that it was easily tripped up by metal contamination and that sort of thing. And because we wanted a robust mechanized method, we shifted to using Gaussian profiles. So the absolute fit is not as good, but it was much more robust and much less affected by metal contamination. So here's an example of the fit. The blue dots are the lines from the 1D image, and then the green is the Gaussian fit that we're doing to it. So you see the Gauss is not, it's not terrible, but it's clearly not getting the wings very well. But the hope is that even with that, if we do things consistently, we can then transform onto an appropriate system. So when deciding what bomber lines to use, we want to be able to get as good a temperature measurement as we can. But what we quickly discovered is that if we plot the equivalent width in H delta compared to gamma, beta, and epsilon, that beta and epsilon were giving not very tight results, right? There's a huge scatter in these points. In beta, well, in both of beta and epsilon, the issue is metal contamination. So at high metallicities in particular, you have these metal lines that are just making that fit not good. So as a result, we stayed with H gamma. So we use H delta and H gamma, average them together, and that's what we consider the bomber equivalent width. Just as a double check, we see that the equivalent width in the bomber lines matches the change in temperature. So it's a pretty decent stand-in for temperature. All right, so we want to take our measured equivalent widths and transform them onto a high-resolution system, but there are many people who do high-resolution spectroscopy. Here's a list of them. And the problem is that no two people agree what the metallicity of a given star is. And so we needed some way of combining all these guys together. So we followed the work of Chadid 2017, and we used Leiden's 1994 paper, which had all of these stars in it. And basically, we would do linear transformations from the high resolution work onto the Leiden system. And that's how we sort of brought everything together. So you can see the best fit and then all the different works that we used. We only did this for the RABs because very few people had done high resolution RRC work. And so there wasn't a good basis set basically to do that transform. So we're going to assume that our transformation from Leyden to the high res is going to be the same for ABs and a C. Okay, so in Leyden's original work, he fit the equivalent width of the calcium line times, equals the coefficient plus the equivalent width of the Bonner line plus the metallicity plus a multiplication of the Bonner line and metallicity. We realized as we were going along that this was not really sufficient and that we had to add on several other terms. And so those are in purple. And we came to this conclusion using the Bayesian information criterion. I can go into great detail as how we did that, but I'll leave for the moment that this was the best form of many, many that we tried. Okay, and so to actually fit our data, or to fit those coefficients, we actually use theoretical spectra using Caru's models. And so what we have here are each of these dots represent, spectra, theoretical spectra between about 6,000 and almost 8,000 degrees Kelvin, between log G of 2 and 3, and then metallicity going from 0 down to minus 2.5. And this is sort of the best fit. Those gray lines are the best fit lines to those data points. And you see that instead of being straight lines like what Leyden have, we have a much more of a curve to our lines, and it seems to do a pretty good job of fitting these data points. Now, if we take the real data, right? So these were theoretical points. We then, pushed our real spectra through the same machinery, and you see that they fall kind of where they're supposed to be. The little lines you see drawn on here are connecting the points that are from the same star going through its pulsations. And so you can see, things sort of move around as they are in different phases of their pulsation. But, their measured metallicity is falling about where you'd expect in this plot. At the end of the day, we mapped, sorry?
Time to be wrapping up.
Okay, yep, I only have one more slide. So this is our retrieved metallicity versus high res studies. And you see that we have a linear relationship between the two. Our slope is a little bit different than the one-to-one line. So at the end of the day, we transformed our relationship back to the one-to-one line. And so if you'd like to have more details, you can look at our paper from the monthly notices. And we have the software available and, of course, the documentation to go along with it so that you can either use our calibrations or you can make your own. There's tutorials to do that as well. All right, with that, I'll open myself up to questions. Thank you.
Okay, let's thank Nathan. And open up for questions then. Let's see in the room first. Anybody got it? Oh, yeah, okay, Bennett.
So, Gaussians work better for your MC model to go model the absorption features. Okay, so why is it? Is it because you don't constrain the actual shape? You put a horseshoe shape. Why is it more robust when you use Gaussians?
So I think that the issue is that the wings of the lines are more susceptible to things like noise, right? Because they're just shallower. And because the void profile is so wing heavy, we would get sort of dragged around, right? Depending on, things like metal contamination or just variations in the flux in the wings. And it's just the fits were not, were not good. Let me rephrase that. The fits were excellent or they were terrible, right? But you don't want an automatic method that oscillates between those two. Instead, we use the Gaussian, which fit the core very nicely. and, was giving basically a, a consistent offset from what the Voight profiles were giving us. And we could do those automatically, and did not have to do them by hand, which was the main goal.
Okay, others in the room here? And what about online? Dirk, can you take a look for those?
Nothing in the chat. I don't know if anybody has a question.
All right.
That's good.
Well, with that, let's thank Nathan again.
All right, thank you.
Okay. And next one up is Lindsay Dawson. We have Lindsay here. Yes, Lindsay is here. Okay, Lindsay, I'll let you hit share screen.
Sounds good.
All right, and I'll give you a sorry here. We got 15 minutes total in principle, including questions, but I'll give you a 5-minute warning and a 2-minute warning on the whole 15-minute block.
All right, sounds good. All right, let's see. All right. Hello, everyone. My name is Lindsay Dawson. I am a senior here at Thomas More University, and I'm going to be giving a little presentation on the work that I've been working on for the past 3 years here on variable sources. So I want to start off with a lot of this work is not necessarily groundbreaking, but it has served to kind of get my feet wet in observational astronomy and the research process in general. I have been supported for 3 years by NASA Kentucky. And so I really got into physics hoping to get into atmospheric science or meteorology, but this research project has really allowed me to find my true passion for astronomy. And so all of our observations were taken at our observatory, the Thomas More University Observatory as well. So the first project that I conducted was on pulsating variable stars. As Nathan mentioned before, pulsating variables are very important with their period luminosity relationship, known as standard candles. And like I mentioned, this isn't necessarily groundbreaking stuff, but it really helped me get my feet wet in astronomical research. And so we observed RR Lyrae because they have short periods. And so we took multiple observations to get an entire period of each of these objects. And we did this for quite a few objects. And so what was really interesting about this particular project is as I was kind of getting comfortable with the research process, I was also incorporating these results into an undergraduate astronomy lab for non-science majors. So they were also able to get a feel for the research process and be able to use real data. And so I've got a couple of examples of targets that we took data on. And so RW draw, this one actually, we believe we're seeing the Blasco effect here. So we're catching 2 different periods of pulsation. So I thought this one was pretty interesting to include. And then we also have VZ-PEG, which is one that's just kind of your standard pulsating variable light curve. The next project that I worked on was capturing transits of extrasolar planets. This was in contribution to NASA's Universe of Learning Exoplanet Watch, which really has the goal of allowing citizen scientists or student researchers or just people with small aperture telescopes. It allows them to collect transits of extrasolar planets and upload their observations to NASA's Exoplanet Watch. And so we really utilized all of the tools that NASA had available to us. They had a specific, I guess, database for targets that were high priority or were observable in our area as well. So we utilized that to select targets for observations. And then once we collected those observations, we were able to utilize NASA's data reduction pipeline, the Exoplanet Transit Interpretation Code, also known as EXOTIC, another very fun acronym from NASA. And this, as you'll see here in the next slide, shows observational data and bin data with error bars, a model of the planetary parameters, and then also ratio of planet to star radii squared, which is an approximation for the depth as well. And so after uploading the data, and after analyzing the data and collecting the transits, we uploaded them to AAVSO for NASA to further publish. And so here's just an example of a few of the transits that we were able to collect. I want to mention that all of these were included in the ephemeris calculations for NASA, except for HAT P52B. As we can see with this data, it's kind of, it's got a higher error on it. The exposure times had to be longer because the object was dimmer that we were looking at. And we didn't get a full transit of that one. But with the other ones, you can see that we have a little bit more error, like a little bit more of the observations with those with shorter exposure times. And then we also have better error, I guess, for those as well. And then I also want to mention that WASP 77AB, this one right here that has the star by it, that one is actually going to be incorporated into a research paper that's in the publication process right now, but it was a case study using WASP 77AB, updating exoplanet orbital parameters using professional data and then also citizen science. And so just a few of the results from this project, we were able to observe 14 targets, 13 of those were published, and 7 of those were included in the ephemeris calculations. With that, we were also able to determine our telescope and camera observational limits. So we found that our depth limit was around 14th magnitude. As we saw in the last slide, one that wasn't included in our ephemeris calculations, that one was around a 14th magnitude. And then our depth limit is between 0.5 and 1%, just depending on the magnitude as well. And then I also have just a target list of objects that were included in the ephemeris calculations, just so you can see kind of what we were able to do with our telescope. Most of them were larger planets that were closer into their star, which makes sense given that, you know, we have a bit of a camera on the smaller side. So that's the data that we were able to collect. And so the project that I've been working on this year is on cataclysmic variables. These were a lot different than pulsating variables and exoplanet transits because they do not vary in a predictable way, and their graphs don't always look the same. And so there are different types of variations with these. You have orbital periods and eclipses that are kind of more predictable. And then these objects do go into outburst and super outbursts, which are the more unpredictable periods. And so for this project, we have been collecting photometry on mostly eclipsing targets or targets that are considered high priority by AAVSO or are in outburst. A variety of these cataclysmic variables were selected, like I mentioned, and then we obtained graphs of nightly photometry in order to get a grasp of their long-term variability and also trying to get trends in their variation outbursts based on published periods. And so we've also observed 4 of these targets and uploaded those to AAVSO as well. So one of the first targets that we examined was B0844 HER. This one was actually in outburst, and so it was being monitored by AAVSO, and they were requesting observations on it because they were expecting to see a 29-minute periodicity with the outbursts and the super outbursts. Unfortunately, we did not see that. We saw more of the 70-minute outbursts. 70-minute periods, excuse me, the 70-minute period, just because I think we were catching it at the end. So this alert first started in July, and we actually got to it in October. And so we're seeing here on the left to the long-term variability. We do notice that it was clearly an outburst because it's getting significantly dimmer as time went on. With the phase data, we're not necessarily seeing too much overlap of trends. This can be mostly attributed to the fact that we didn't necessarily get it in time. And also a rookie mistake that I made was for the dimmer nights, night 3 and 4, I didn't necessarily increase my exposure times. So I wasn't probably getting as quality data as I could have been with that as well. And then the next object that we took data on most BZ KAM. We started taking observations in November. And this one wasn't necessarily an outburst or anything, but it's known to do some interesting things with strong variable outflows. And so we are seeing a little bit of variability in the long term of it. And then also we are seeing some overlap in the phase data. Dr. Ryle also likes to joke that I don't observe late enough to see interesting things. But there isn't enough to say that conclusively we're seeing overlap here. But it's an object that probably would have needed a few more observations to determine that as well. So for the future, there's not a ton of time left in the semester, but there is another alert out that's requesting monitoring of 11 dwarf novae in support of Hubble Space Telescope. And so this alert is not necessarily to take a look at outbursts, but it's taking a look to make sure that these objects are not in outbursts going into HST observations to ensure that some of the HST elements are not damaged if these things are in outbursts or they're a super high magnitude. And that's all I've got. Thank you guys for listening, and I'll be happy to take any questions.
Okay, let's see if there are questions in the room here first. Yeah, Bennett has a question then.
You said it was supported by Kentucky, so did each of your project get grants to support it, or was it just one hard one? What did you do?
Yeah, so Dr. Ryle actually has been great helping to get the grants, but each year has been separately funded. And so basically each year has the same theme of variable systems, but each year have had different funding from the NASA Kentucky Grant Consortium.
Science every year. It's pretty impressive.
Mm-hmm. Other questions? Yeah, Kyle.
Yeah, so kind of springboarding off what was just said, you did basically 3 different projects in 3 different years. You said it kind of awoke your passion for astronomy. Which project, if you could pick one of the 3 projects to continue, which is yours?
Oh gosh, I've always said that I love the exoplanet project. I just think it's super cool to, have the opportunity to explore planets that aren't in our solar system. And so that's a project that I would love to continue, especially since I actually went to AAS in New Orleans and I was able to meet the person that the paper that I'm on that I mentioned. And he's, using Exoplanet Watch a lot. So I think that that's probably the project that I would like to continue, especially just continuing with the citizen science portion of it as well.
Nathan has a question.
Yeah, question from Nathan.
Yeah, first, great talk, and this is very exciting because, at NKU, right down the road, we have an observatory that is patterned off of your guys' observatory. And so I'm just really excited to see that you guys have been able to get, good data through this. We've done some work with exoplanet follow-up in particular and have seen similar sort of results. So, I'm hopeful that we'll be able to get more folks sort of following your guys' footsteps. And I might contact you all later to talk a little bit more about the Exoplanet Watch and Exotic, because I think those are tools that I very much like to learn more about.
Yeah, absolutely. And I mean, NASA makes it pretty easy to understand all those things. And so, yeah, we definitely be willing to talk with you about that as well.
Wonderful. Thanks.
I've got a question as well. Going back to your exoplanets, what was the size telescope you were using for those?
Let me go back to my first slide because that has all of the information on the camera that we were using. Yeah, so 11-inch Celestron, and then we also had the S-Big camera with the self-guiding filter wheel.
Okay, it really does blow my mind how the discovery of transiting exoplanets back about 2004, I believe, which was originally done with a somewhat larger but still relatively small telescope, has just opened it up for even amateurs now, to say nothing of undergraduates and professional work on being able to observe exoplanets.
Well, yeah, the same thing now with CubeSats. I mean, there was the whole thing with Asteria, which was a 6U CubeSat that we monitored for more. There was a JPL mission.
Yeah,
And it was just mind blowing because there was Kepler, right? I don't know, $1 billion mission discovered exoplanets, but we can do it with Asteria and confirm those exoplanets. It's just, wow. Right, here you are, this with an 11 image, and look how many images have that.
yeah. This is great. Any last questions then? By the way, you got a nice comment there from Jerry Williger on nice talk on exoplanets and variable stars, which indeed it was. Okay. Let's stop the timer there. Next up, we've got Ash Coleman. Oh, and let's thank Lindsay again. I'm sorry. Yep, sorry. Okay. Ash Coleman. Do we have Ash Coleman here?
Yeah, I'm here, sorry.
Okay, there you are. There you are. All right, now I'll give you you've got 15 minutes total. I'll give you a 5-minute and a 2-minute warning then.
Okay. So
All right.
Okay. What are you guys seeing the presenter view too?
Yeah, you'll have to flip it.
Oh yeah, we're seeing the next slide as well as the current one.
Okay, how do I?
Usually it's the upper, for me, it was an upper left-hand corner. Let you flip, which was
The
which.
use slideshow maybe?
No. Maybe use slideshow. That this may be a different type of machine. Oh, there we go. That
There
looks
we go.
right.
Oh,
Yep.
I can. No, I can't see the presenter view.
Out of that, and, are we unmuted?
We're unmuted.
Okay, yeah, so to close out of that, and then on PowerPoint, go to,
What is it?
so slideshow, there's a menu, I think.
She's in the slideshow
There's a
menu.
place, okay. Is it under setup slideshow? I think you can like switch the presenter view and like switch the, that's the, switch the monitors, see?
Slideshow monitor at the bottom.
Yeah. So how many monitors do you have, Ash?
This one.
Ah, that's the problem. You can't because you're sharing your screen. We can only see what you see. In my case, I had 2 screens, and so I could have the presenter mode appear on the other side.
Okay.
But because you're screen sharing, I'm afraid you're gonna be stuck in.
That's
yeah.
Okay, well, we'll just have to make do.
It's fine.
All right, go ahead.
All right. My name's Ash Coleman. I'm a fifth year senior at Thomas More University. This is my culmination of my research that I've done over the past few years here at Thomas More. I'll be talking about 3 different eclipsing binary star systems. I'm sure everybody as an astronomer has heard of those. But you may be wondering, okay, cool, what's so important about eclipsing binaries? We use them to measure the basic properties of high mass stars with high precision. When they're out there by themselves, it's a little more difficult to get that information. But when they're eclipsing binaries, then you get the you can get like individual parameters as well as if you have radial velocity data, you can get individual parameters. I'll be talking about, we use the Phoebe software, physics of eclipsing binaries, to run this process. So here's just a couple of the parameters you're able to get just from this basic eclipsing binary light curve. You're also able to get the out of eclipse shape will show the tidal distortion. of the stars. So here's the first one that I've looked at. It's DR Vol. This one is kind of interesting because it has apsidal motion, which suggests the possibility of a third or even a fourth body outside the system. This was proposed as far back as 1986, and even as recent as 2007, and probably more recently, but I wasn't able to find a whole lot in the literature about that. Our singular light curve does not give us any information about this companion star, but we do get some further like just verification that this is an eclipsing binary. And if we are able to compare this over years of data, we can possibly start to see some verification of that apsidal motion and possibly some comparison, and able to see if we can find those third and fourth body parameters. And this is, we've run a Monte Carlo, or a Markov chain Monte Carlo process, sorry, on the data. And we also get it's run through Nelder-Mead as well. That's just a function minimizer. You aren't able to get any of these parameters individually. You have to find them all together because they're so interdependent. So we have to run them through that Markov chain Monte Carlo. The best way I've heard that described is just like a large scale statistical method for guess and check. But these are still preliminary. We do need to explore parameter space and do more iterations, but computing time and power is quite a hindrance. We're running this on a laptop over many days. The next one I have is LS3 plus 6212. This was proposed to us as a possible eclipsing binary. It is actually categorized in SIMBAD as simply a star and not as an eclipsing binary yet. So we believe we may have preliminary first parameters of the system. Because I also went kind of searched through the literature, and all I could see were just catalogs that included this star. So we have our data, and again, our very preliminary parameter estimates. We did the same thing here. It's the Monte Carlo Markov chain process. Again, hindrance of computing time and power. The last one that I'll get to is HD 51082. This was also given to us as a possible eclipsing binary. It is categorized correctly, unlike the other one in SIMBAD. However, there isn't any information on its parameters within the literature. We also have not only gotten the Thomas More R filter data, but we also have ASAS V filter data, and we also got data from the US Naval Observatory for radial velocity, so we were able to determine preliminary individual star parameter estimates. And so this is ASAS V filter, TMU R filter, and these are, since we had two sets of data, we could add a couple of extra parameters down there. They're just luminosities for vertical scaling on the data. But again, these are very preliminary. We still need to do some more exploration. But we also have the US Naval Observatory data. This is radial velocity data. You'll probably notice the slight oddity that is the more massive star being called the secondary. I will get to that in a minute, but oh no. Okay, there we go. These were the models that my advisor, Dr. Ryle, was able to find or to get through the Phoebe program. And we've also got on these some uncertainty. And these are just, I wanted to compare them to the US Naval Observatory, because this is from TESS. We got TESS models as well. And so that's another set of data to compare. And I just wanted to compare those to the sets of data that we have. Here's our data from TMU, ASAS, as well as TESS. So we have two sets of data. They seem to agree with each other, which is great. We love to see that. And but we again see TESS is a little more precise just because we have an 11-inch telescope here at TMU. But I'll get back to this oddity with the mass. Even if we put the data in backwards, like we labeled the other stars, the primary, we still get this exact same data where the more massive star is considered the larger one, or is considered the secondary one. And if you look at the uncertainties, these stars are so close in mass that they are almost the same. And so we believe that the radii may be switched, but the more massive star is the larger one that has evolved slightly. So overall, what's next for us? Again, as Lindsay said, there's not a whole lot of time left in the semester, but for DR-Vol, we've got that possible we've got that apsidal motion that has been seen by other astronomers and the third and fourth body problem. We would like to further, and we've gotten the further verification and parameter estimates. If we can find some data over the years, it would be nice to see if we can start to see those parameter estimates for the third and fourth bodies, but we'll see if we can manage that. And then for LS36212, we've got that verification, the preliminary parameter estimate, possibly the first estimates that are out there. Same with HD 51082, and we've also got the comparison to TESS. But overall, we really just need to do more iterations and explore more parameter space and just get more data so that we can have some more comparisons. And that's all I got for you guys today.
Okay, I've got a question to start off here. Looking back at your star LS36212,
Yes.
you said that that one was not shown in SIMBAD as being an eclipsing binary. How did you find out that it was one, or why did you look at it to begin with? What was there one team that had seen this evidence, but it just hasn't been put onto the onto SIMBAD yet, or what?
I believe it was proposed by my advisor's contact at the U.S. Naval Observatory to be a possible eclipsing binary, and so we just decided we picked that one to explore and see if we could find that, because you get that very specific light curve from eclipsing binaries, and you can see that in our model. However, we are missing the out of eclipse data, so we would also like to take some more data just to verify that we've got that as well.
Uh-huh. Okay, yeah, it certainly looks like the model fits it very well.
Right.
Other questions? Let's see in the room here first. Okay, anybody online? Dirk, you're looking online there? Okay. Nathan, why don't you ask?
Yeah, well, again, very nice presentation. I feel your pain with Phoebe, trying to get it to fit things in a reasonable amount of time is always an issue. I know for myself, I often ran into issues with the fits running off of the stellar template ranges. So like they'd get too cold or too hot. Did you run into a similar situation where, you know, for a given system, it would the Monte Carlo would just fail? Or is mostly what you're running into are that you just don't have enough time to do enough iterations to get you know, a good approximation to the error bars?
I did not have any failure or issues with the iterations that we did run. I can't speak for the test models because I'm not sure, because my advisor did those, but the only issue we really ran into was other than like the weirdness with the masses and the radii, and that last one is not having enough time or power to just keep running.
Right. Okay. Thank you.
All right, any others? Okay, well, with that then, let's thank Ash again. And our closing talk for the conference is Wes Ryle himself. Be talking to us about the Cincinnati Observatory and its history. Sorry, close the what?
Stop sharing.
Can you stop sharing?
Yeah, there she is. Okay,
All
Wes,
right.
I'll give you a 5 and a 2-minute warning and take it away.
Sounds good. Thank you all so much. So one of the advantages of making the schedule is that I could put myself last here, and so I can just talk as long as I want to. That's how it works, right, Tim? Before I get started, Tim, for you, I wanted to show you, this is actually something Ash got me this year. This is a little stuffed tardigrade. And so they do have toys that are available if you were interested in stuffed tardigrades. So I'm going to talk a little bit, change of pace, a little bit of a history talk here about the Cincinnati Observatory. They like to call themselves the birthplace of American astronomy, and so hopefully I'm going to be able to convince you of that here today. It really is, I'm hoping to convince you, kind of a national treasure that's here in our region, and if you haven't visited, I'm going to definitely encourage you to do so. I've definitely got ulterior motives in terms of giving this talk, and I'll mention those here in just a second, but I want to kind of convince you about why the observatory is unique, kind of its role in terms of American astronomical history, and then what they're doing today at the observatory. So some of you that are in the kind of administrative council for the Kentucky the Kentucky Area Association, Astronomy Association. So I mentioned this earlier, but I've actually accepted a position as the astronomer at Cincinnati Observatory, and I'll be starting there in summer. And so I'm actually going to be leaving Thomas More. I grew up in the area and actually never knew about the Cincinnati Observatory growing up, even though I had an interest in astronomy from a very young age. After I started here at Thomas More, I began volunteering there in 2014, and pretty much the second that I stepped foot on site, fell in love with the telescopes, fell in love with the history of the facility. And I think that pretty much any professional astronomer that you bring on site is probably going to be able to do the same. One thing I do want to mention is that even though I have accepted that position, the public announcement to the media hasn't actually been made yet. And so don't share that too widely. I don't think any of y'all are going to do like a press release about that or anything like that. So there's not really a worry there. But it hasn't been announced publicly. It's going to happen after the eclipse. And mainly what I'm trying to do with this talk is to help raise the awareness of the observatory in the professional community. They're really good in the local region, but not so much necessarily nationwide, and not so much in the professional astronomy community. And so first off, the location of the observatory. The original location that we'll talk about that was built back in 1843 was very close to downtown Cincinnati. If you're familiar with Cincinnati, there's 7 hills that surround Cincinnati, and they all have their different names. Mount Adams is one that's very, very close on the east side of Cincinnati, where the original location was at. And then in 1873, they had to move out to a location that at the time was out in the country, but now, of course, is in the suburbs of Cincinnati. And they did that move in 1873 for reasons that we'll talk about in a little bit. So the reason that we call this the birthplace of American astronomy is because American astronomy was definitely something that was lagging behind our counterparts in Europe and Russia in the early to mid 1800s. There was actually an effort by the 6th president of the United States, John Quincy Adams, to make a national observatory. And this was mainly based on the fact that he had spent time as an ambassador to Russia, spent time in Russia in his early career, and toured a lot of the observatories that they had in Russia. And he noted that Europe and Russia combined had, at that point, dozens of observatories scattered all over the place, and the United States did not have any official observatories. He sought to fund and build a national observatory, but this was definitely during a time where states' rights was a big thing, and Congress didn't want to support any kind of federal initiative to make a national observatory. That leads us to the founder of the observatory itself, a gentleman by the name of Ormsby McKnight Mitchell. He was actually born in Kentucky and raised over in Cincinnati, or just outside of Cincinnati. and was a very bright and independent individual, especially during his youth. He actually declared himself independent around the age of 13, and worked to help support his family after his father had died at a relatively young age. He learned of West Point Academy, sought letters of recommendation from some of the big names in Cincinnati and Ohio at the time, and was appointed to West Point Academy at the age of 15. Had to travel there on his own, mostly by foot, in order to get up there, but was a pretty successful student at West Point. There he learned mathematics, he learned astronomy, and that kind of led to his passion for astronomy that came later in his life. After teaching at West Point for a while, after his graduation, he actually returned to Cincinnati and picked up a position at Cincinnati College, which would eventually become the University of Cincinnati. And as part of this, he was teaching courses in mathematics and astronomy. His students loved his lectures, his astronomy courses, so much that they actually asked to invite friends and family to his lectures. And based on this, he decided to actually start having public lectures. And so he held those in Cincinnati. The first couple might have had a few hundred people in attendance, but very quickly word spread. And by the end, he was hosting public lectures that had over 2,000 in attendance, the largest lecture hall in Cincinnati they had to use in order to host his lectures. Realizing that there was that public interest in astronomy, Mitchell actually helped to form the Cincinnati Astronomical Society. And the purpose of that society was at the time to help fund the construction of an observatory in Cincinnati and the purchase of a telescope. And this was crowdfunding. This was early door-to-door, asking folks if they would be willing to invest in $25 shares to fund the construction of the observatory. And of course, he was doing high-profile names in Cincinnati, but he was also doing just common folk that had interest in science that were willing to give up what was at the time a very large portion of their yearly wages, $25, in order to support this initiative. When he had raised sufficient funds, he actually traveled to Europe in 1842 and found an 11-inch lens that was designed by Fraunhofer himself and sold by the Merz and Mahler company. It was actually a backup lens for one of the telescopes that they were building in Russia at the time. And so it was very, very high quality, one of the best lenses available at the time. Obviously, you had to go to Europe to get those really good lenses in the mid-1800s. And the observatory itself began construction in 1843, and we bring back John Quincy Adams because of his interest in a national observatory. He was actually invited to help dedicate and lay the cornerstone for the observatory when it was built in 1843. This is actually the original location, again, in Mount Adams, in the original building. It had offices on the first floor, residence on the second floor, and the telescope there at the top. Obviously, not something that you necessarily want to do with your observatory today, but it was located right there down close to Cincinnati itself. You can see in the picture at right the steamboats on the river there. And so, while the observatory was started construction in 1843, the actual telescope itself was shipped across the ocean, shipped up the Mississippi, shipped up the Ohio, and eventually arrived in Cincinnati and was installed and saw first light in 1845. And this is now named the Mitchell's telescope after Ormsby Mitchell. So 11-inch lens, 16-foot tube. This is an artist rendition from the very early days before photographs. But here's a photograph of the telescope itself. And I think you would be hard pressed to find a more beautiful telescope. That's mahogany and brass in terms of the construction there. And they have done exceptional work in restoring things as much as possible to the original specs that the telescope had. This one actually does run off of an electric drive, just to make things a little bit easier. But the other cool thing to keep in mind about this telescope is that it's the one that we use for public nights. Lindsay actually works as a intern at Cincinnati Observatory, and her and I were just there last night for a public night where we were using this to look at the moon and Jupiter. It's been in nearly continuous use and available to the public in 1845. It's had a history, because it was crowdfunded, to always make it available to the public. And so what's really great is that we can tell folks that they're using the same telescope that 7 or 8 generations of Cincinnatians have actually used when they're making those observations. And there's the inscription that you can actually see that was designed by Fraunhofer and sold by the Merz and Mahler company. Now, they had to eventually move out of the city just because by 1860, Cincinnati's population more than doubled. There was a lot of burning of soft coal in downtown, so there was a thick layer of smog and smoke over the city, and that essentially made astronomical observations impossible. And so in 1873, after being acquired by the University of Cincinnati, it was moved to its new locations a few miles away on Mount Lookout. This is the building that is currently still there with a different dome. So that's actually a cupola that has now been replaced by a metal dome. In 1904, they were able to acquire a larger telescope, so 16-inch objective lens, 22-foot main tube, metal construction in this case, that's now housed in the main building. And they have an additional building that is housing the original Mitchell telescope now. The Alvin and Clark's telescope is still functional, still operational. And again, it's beautiful that the gravity drive and gear train on this thing is actually still original. And so just like last night when I was given a tour, you can have kids come up and pull that crank in order to lift these weights off the ground. And then those weights pull on a governor that spins and drives the gear train for the entire telescope to have it track at a sidereal rate. And so it's not an electric drive. There's no electricity involved at all. Still running on the original gravity drive and still operational, still used for some events on occasion. So in terms of significant contributions to astronomy from the observatory, Mitchell did work on identifying double stars. And so he was actually one of the first to indicate that Antares was a double star. He did precise longitude work. So one of the first measurements, the first measurement of the precise longitude of Cincinnati. And he even did some observations of Mars and mountainous regions at its South Pole. He also started a publication, one of the first kind of both scientific and public knowledge kind of publications called the Sidereal Messenger. And you see a copy there, a monthly journal devoted to astronomical science that he served as editor for. His wife, who actually helped him with a lot of the observations that he did at the observatory and even did the observations herself, was also likely one of the first Americans to observe Neptune after its initial discovery in October 18. She observed it in October of 1847. The second director, Cleveland Abbey, was actually by his time, pretty much foiled by the pollution in Cincinnati. And so not a lot of astronomy contributions, but because he couldn't do his observations, he actually got interested in pioneering weather prediction. And so the telegraph was becoming widespread in terms of its use. And he was one of the first to realize that he could message somebody in, say, Chicago or somebody in Denver and get what their weather was and be able to say, oh, well, weather appears to head west to east in the United States. I can get a pretty good idea of what the weather will be like today based on what it was in Chicago yesterday or what it was in Denver 2 or 3 days ago. And this was very valuable, right? This caught on very quick, especially for military applications. And so the national government became very much interested in it, and he went on to found the National Weather Service. One of the later directors, Paul Herget, was actually the initial director of the Minor Planet Center. And the Minor Planet Center was actually headquartered at the observatory for a significant amount of time for most of Paul Herget's career as the director of the Cincinnati Observatory. And he was also one of the first to use calculators in terms of computing orbits of asteroids. Or I found this picture, which was really interesting. This is an article that was written October 6th that you see there, but you might be able to guess the year. It's talking about Sputnik, right? And he was one of the ones that were doing calculations of Sputnik's orbit shortly after it was launched. And so he was able to use observations at the observatory plus his very, very early computers in order to be able to calculate its altitude and its orbit. So today, obviously, we're not doing scientific observations at Cincinnati Observatory. We are kind of exploiting the fact that it is this beautiful historical facility that has a rich history in terms of sharing with the public. And so today, it's mostly about education, engagement in the community, and outreach in the community. And so we have lots of K through 12 school groups. We have public nights. But one of the things that I'm trying to encourage again is more awareness in the professional community and even more awareness on the national stage, right? You hear about historical observatories like Lick Observatory or Mount Wilson or Yerkes or things like that. But we're really trying to make Cincinnati Observatory a little bit more well-known, and make that history a little bit more well-known on the national stage. So hopefully you learned a little bit of something about Cincinnati Observatory. If you haven't been there, again, I'm going to highly encourage folks to try to make their way out. I'll be starting there part-time in May and then full-time in June. And so I'll be in excellent contact in order to be able to set up private tours or anything like that. And like we mentioned yesterday, this might be a site where we can actually host a meeting, if not next year, then probably a couple of years down the road. So the website is there. There are Facebook, Instagram, and YouTube outlets available in terms of information as well about programming and general information. Thank you all so much.
Okay, well, that's certainly a way to end up the meeting. Any questions from here in the room? We got one from Dirk.
This was great. I was at the observatory, gave the talk in October last year, and one thing I learned when I gave the talk there, when they introduced me to the observatory there. First of all, I had no idea that this was the oldest observatory in the US. Second, in the 1990s, they almost lost everything because they wanted to build an apartment complex. Yeah. And, fortunately, this was prevented, and it's really a nice site. So hopefully, I think the plan might be next year we're going to Berea. Maybe Charlie and Tracy can talk about that briefly, but we should go to the observatory, I think, in 2 years. Yeah, I mean, it's a nice room. We will fit all in there. I mean, given in particular this size of this meeting this year, but it fits about 50 people. Okay, so it's a nice facility.
That would fit us. Yeah.
Should definitely fit us.
I think it's a good attraction to bring people into it as well.
So,
Yeah, minute.
Two questions. One is this is available for, let's say, small astronomical meetings, for example? Because a friend of mine runs your keys now, and I was asking if you could, like, she has it open for what is it called? Retreats and stuff like that. But it's like, when I have a meeting there, great if we can have a Kentucky area meeting, but suppose I want to have a NASA meeting in Cincinnati. Cincinnati is an easy place to get to, so I can have a national meeting there, for example. Is it open for rentals? Is the question?
So yeah, they have been open for rentals in the past. I mean, they even do things like weddings and receptions and things like that. And so they are definitely open to working with groups in terms of being able to host an event. Keep in mind that, like Dirk was saying, that in terms of space, it's a limited amount of space in the two buildings. And so there are 2 large classrooms in each building, but the max capacity is something like 40 to 50 in each of those rooms.
Workshop, right? This is the kind of thing where I just want to cram everybody in a cool room, and this is it.
That's definitely good for that. And that's one of the things that I'm hoping that my working there is going to kind of improve is drawing in more folks from the professional community to kind of get more exposure.
And do you have public talks? Do you need people for public talks?
So they typically have a public lecture every Friday night. Like I said, Lindsay and I were just working one last night, and I was giving a public lecture. And then they do special events on Saturdays or Sundays when there's big events like when Jupiter's nice and visible. They have a Jupiter night, and then they have a Saturn day, and then they have during the summer they usually have a Sunday event where they have food trucks and ice cream cones and things like that, all while going solar observing. So yeah, the core mission is really exposure to the public and public outreach.
Yeah, in the back there, Steve.
Yeah. Do you have any idea you are gonna do the meteorite nights again?
Right, Meet a Meteorite Night. It's one of the events that they would regularly have, and I do believe there is one scheduled for later this year.
Okay, because we missed it last year.
It's definitely a fun event, especially for the younger crowd.
Yeah.
Others in the room here? I was going to say I'd been over there a few to several years ago, and Dean Ream gave me a tour of it after we'd met at some event, and it really is gorgeous. I was also surprised to find out that it was tucked away here, not too far away from us. Any possibility of, say, bringing student like astronomy classes over there? Is the telescope used even for like public viewing nights?
Yep. And so every single public viewing, as long as it's clear, we're using the original 1845 Mitchell telescope.
Okay.
And it's really great because it's something where, I can let 5-year-olds, 6-year-olds, 10-year-olds come up and touch and move the telescope, turn the crank to move the dome, turn the crank to pump up the weights. And so it's very, very hands-on. And that's something that I think is unique. It's one of the things that they advertise is that it's one of the oldest telescopes in the world that you can probably actually touch, right? That you can actually get your hands on. And so, yeah, we're definitely open for that kind of thing.
All right. Well, I'll be seeing about maybe organizing an astronomy class field trip.
Absolutely.
What about online questions then?
I don't see any.
Jerry, I saw your comment. Yeah, and I'd love to do an astronomy on tap. So I imagine I'm going to be doing a lot of those pretty soon here.
Okay.
Before we close, Gary would like to talk about the eclipse.
Okay. Yeah. In fact, I was going to say if Jerry hadn't done that, I was going to say we need to be mentioning the eclipse here. So, Jerry, could you?
Right. Well, okay. I think the thing to do might be to run around the room a little bit and just let each other know what we're doing. Sort of me personally, I have created an Eclipse course, which is online. It took an enormous amount of time to get the approval for a new course number and go through the committees. And then I gave an in-person 9-student version last semester, and I made it up as I went along. I can put the URL here if you want to take a look. About half of it is science. Oh, darn. Yeah, our server's down. Let me put it in here. I'll have to type it in. Half of it's on science, and then I ran out of material because you can't fill up 14 lectures about the nuts, and it's just too hard to fill up in a 100 level course. There's the URL. Our server will be up in a day or two. I hope we're moving buildings because we're having renovations. I now have 100 people in an online course, and interestingly, only about 40 of them are regular students. I have 8 high school students, and the rest are either faculty, staff of the university, including the Dean of Public Health. We have the Dean of Public Health in our class. He loves astronomy, and he's a champion of astronomy. Benny, we have an advocate on the dean level, but in public health. And then the rest, I'd say about 30 to 40 people are retirees because they don't pay money.
Thank you so much for your help, though.
Yeah, they don't pay tuition, and so we got them in.
We'll
what
go
I'm going to
that.
do is write a paper and then be ready. I gave away the slides. As a matter of fact, let me give you the GitHub here in the chat, and you can take the slides and you can edit them. They're in PowerPoint. Let's see here. It took about 2 months to write this. It's about 3 days per lecture.
That sounds like it's
lectures.
going to be just a horrible tasting vomit after.
It was
Hang
a lot
on,
of
Wes,
work.
I think you got a hot mic there.
Yeah.
Okay.
Oh, I hope that wasn't a response to my Eclipse slides about the.
That was me talking to students. I'm terribly sorry.
About the.
My bad.
You have a situation there. So yeah. All right. There. Okay. Here are my slides. You can take them. You can do anything you want with them. You can edit them. I only ask that you please acknowledge me and tell me what you did. I've given them away to everybody that I can think of, and actually nobody has said I've used any of your slides, although I suspect maybe people did and just forgot to tell me, because I want to write a paper and say the slides were useful and have something ready for 2045. I hope to be alive and kicking in some way. So that's what I'm doing. Our campus, our Society of Physics students is discussing things to do to go on an outing to Bloomington. A major problem, and Bennett, please say what you can. Our planetarium is closed. And so our outreach is, I've been giving talks. I'm sure Benny's been giving talks. Liz's been giving talks. A number of people have been giving talks in town. But because our planetarium is closed, we are limited in what we can do. I'll leave it to you, Benny, and everybody else. That's what you're doing.
I can go real quick.
Unmute
I
you.
can apologize for that. I was joking around with students. I actually managed to get the administrators to cancel classes for the afternoon, which was
We
nice. I
didn't.
still worry that, students won't necessarily be able to get too far if they're leaving around noon, but hopefully traffic won't be that bad. But we're not having an event on campus because at 99.5% or whatever we're at, I don't want anyone here. I want them to try to go to totality. And I actually made a commitment with some of my friends and colleagues 7 years ago after I made them do the event for me as I went to go see totality. They said this time we're going to a spot, a family farm that's just outside of Dayton. I will be doing some live streams and things like that with groups, both with the Cincinnati Observatory and with Thomas More, but kind of a small private group for me.
Let's see here. Yeah, Christine, you want
Yeah.
to speak now? Go
Yeah.
ahead. You're on camera.
All right, so I've been working on this, excited about this. I'm hosting a party up in Findlay. We get 3 minutes and 3 minutes and 45 seconds of totality. I'll be at a school. School's closed for the day. They're opening it up to the public, to the community there. And then we're gonna bring our people. We're having lunch. I'm setting up like a festival. We'll have different booths with, demos of projection methods. We'll have some crafts, like making an eclipse mask for kids, where you take a paper plate and, cut a triangle for the nose and you stick the glasses on there, let them decorate it, right, so that they don't accidentally see the sun. Decorate sun cookies. All sorts of fun stuff. I'm gonna bring my portable up, stick it in the gym. Of course, have telescopes, binoculars, all sorts of stuff. And you have to drive yourself, but it's $20. And that includes lunch and all the cool things.
Mhm.
So,
And lunch.
yes, and lunch. And you can add dinner if you want. But yeah, that's what we're doing. And it's
Okay.
open for
And
anybody.
that's what location again?
It's in Findlay,
Findlay,
Ohio.
Okay, and that's up
Yep.
near Lima, up,
Lima,
up,
north of Lima.
yeah, okay.
Yeah,
Okay.
it's kind of in the middle of nowhere. So I mean, I've looked at eclipse traffic predictions. There's a lot going towards Indianapolis.
Mhm.
There's not too much going north. I mean, still, I'm suggesting people leave at 9:30 from Cincinnati to get there at 1 for lunch, even though it's usually a 2.5, 3 hour
and
trip.
predicting, moving
Yeah.
along, what I saw last time
Mhm.
with, looking at the traffic leaving, after the
Mhm.
eclipse, which is usually gonna be more intense than going
Yeah.
to it, because people might arrive much earlier.
Right.
But I took I don't have it on this computer here, but I took a snapshot of the US traffic conditions on Google Maps,
Oh.
overlaid the, eclipse path.
Uh-huh.
And what I found was that, because I didn't think to do it until 8 hours later, there were hundreds of mile-long traffic jams with red
Yes.
and some orange, but they were all radiating out perpendicularly away from the eclipse path, which makes sense, right? Because no one's gonna go parallel to the eclipse path, mostly at that point. You want to get to the closest part to you. So if you're traveling, you were saying like from
Mhm.
Cincinnati up, if you're traveling from Cincinnati up that way, then you're probably, because you're already close to totality there, you
Yeah.
might not really have that bad traffic. I wouldn't
That's
count
what
on
I'm
it, but
hoping.
yeah. But traveling
Yeah.
along that line is going to be the best traffic.
Mhm.
Yeah.
Well, relatively speaking.
Relatively speaking,
Yeah.
right. Not
Yeah.
quite as bad as elsewhere, I should say.
Yeah.
And the problem last time was also E-Town, because that was the problem.
It was that what?
E-Town, because you have 65 Louisville down to Bowling Green, and then you have the Western Parkway hitting and the Bluegrass Parkway hitting, and that's where we got stuck. Because some of my students, when I was in Moorhead, were stuck for 12 hours. That was really a problem.
Yeah.
Because then everybody from Indianapolis, Cincinnati,
Mhm.
Columbus, Ohio, they were going that way.
Yeah.
And,
Yeah.
this time we don't have that, because when we are in Findlay, it's straight south. You
Yeah.
go around,
Mm-hmm.
okay, maybe you have a little bit more traffic into Cincinnati, but Cleveland coming from their
Yeah.
side. We don't have to worry about Cleveland. We don't have to worry about Detroit, Toledo, even Columbus, Ohio. They are going to the direction. So we could.
Yeah. And,
Alan,
Yeah,
Yeah.
so go ahead, Alan.
Okay, so here at Austin P, we're not in the path this time, so we need to travel a little. Dr. Buckner, Spencer, is going to stay actually on campus because he's like, well, I saw one eclipse and 98% is good enough for me. But he's going to be on campus doing public tours and public lectures. Our student club is transitioning from here to, they're trying to get across the river at Paducah over to central Illinois. They're aiming for Carbondale, but somewhere from the maximum security prison at Marion on over to Carbondale. That's where they're going. I'm loading up in a car with the head of the ag department and about 5,000 crickets. And we're driving down to Uvalde, Texas, and we'll be setting up with the NASA Marshall Solar Physics Group at Uvalde, Del Rio, and Eagle Pass. All three places in the news. We're talking to grade schools, high schools, middle schools, community college, a technical school in Mexico just across the river. And we actually are setting up the cricket experiment and public outreach on the day of the eclipse at Garner State Park, just outside of Uvalde. And it turns out they have a ranger named Cricket. So Ranger Cricket is going to help us do the cricket experiment. And so it gives us, among other things, an excuse to miss 5 days of courses. And the chair of the ag department also misses the accrediting review for their vet tech program, which he's so upset about, but that's what we're doing. And we'll have a couple telescopes with us, and no science per se. It's more like going down, taking pictures and having fun this time.
Yeah, as a friend of mine, Mark Cocte, has said in some of his public talks about the eclipse, he's at APL, Johns Hopkins APL. His big piece of advice is when it gets to the eclipse time, make sure you're looking at the eclipse and not looking at your equipment.
Yeah.
Up to run automatically, learn what you need to do in advance then, but you want to be able to enjoy the thing.
Yeah.
Yeah, I should say we have actually canceled all of the physics and astronomy classes for the day of the eclipse. And the dean is considering canceling all of the College of Science classes for the day of the eclipse.
Mm-hmm. I'm actually telling my students that I would encourage them to take the day off and drive up to Dayton or wherever they've got any family, friends, or just a place to pull over in a Walmart parking lot and do it. I'm canceling my class because I'm heading to Texas as well. I was hoping to stay with a cousin of mine in Dallas. It goes right over her house, but she's got the 2-year-old there and no spare bedroom. And but she said, come by and see me when you're in, if you come. Then I talked to Ohad Shimmer, who's a astronomy professor, you know him, yeah. And he said, well, I've got a spare room, but I've already promised it to another astronomer. But come by and, we could do something, some outreach if you're here then. So I got 2 people who want to see me and know where to stay. And I was just about to go just camping when an amateur astronomer in Pittsburgh I've been working with on some filter designs asked me what I was doing. And I said, well, bedroom ideas have fallen through and I don't want to spend $500 a night for the hotels. So I was going to camp. And he said, well, we've got an Airbnb and my daughter-in-law said she can't come now. So we got a spare room. So come with us. So I'm heading down. I'm canceling my one class. But Maria Christina is getting back from an APS meeting in California the day before, or 2 days before. So she doesn't have time to meet with me, to come down with me. So she and our younger daughter are heading up to Dayton if I can, and hopefully I can get a hold of our friends in Dayton and see if they can come over to their house.
Yeah.
Okay, so I'll make a note about that then. Yeah.
Yeah, I have some flyers.
Okay, yeah, please. Mm-hmm. What do we have? Anybody else who's got either activities going on or trip going on?
Texas.
Yeah, Joseph, where are you going in Texas?
Houston, and then driving up to Waco.
Okay, Houston to Waco. All right, are you flying into Houston or are you driving all the way down there?
Flying into Houston, renting a car, driving up to Waco, returning the car, like renting the car for like a day or two.
Yeah,
And returning it back to Houston.
okay. Are you bringing any cameras or equipment with you?
Nope. Just going.
I'd recommend, at least if nothing else, get your iPhone out on a little tripod and set it on automatic and take a time lapse.
Okay.
But it's worth getting something, but you don't want to be fiddling with it during the eclipse.
Yeah.
Yeah, Bennett.
I'm going up to up 64. There is a lake just off 64 where one of the people that is in our board of trustees or was in their board of trustees, I'm not clear on that, but she's having a large event for friends and family. So me and another colleague are going up there to be the edutainment, which, you know, great. But also she has it all organized, including lunch and breakfast and all that stuff. So my plan is to do the same thing I did in the 2017 one, which was you can set up a camera, and if you take a landscape picture, and you have it up with the timer, and so it takes a picture every 3 seconds, and so you then replace every column with a picture from 3 seconds later, so you get a time lapse as you look across the that's cool. It's really neat. It's called the Overshadow Project. It was done by the photography department, and so they were on the line of totality. We weren't as organized this time, so I just directly asked the Brit who built the software for the camera. So he's shipping. So and I'll be at a very picturesque, Illinois lake. So like, at least I can take a decent picture of that. And like, I was looking for I was at Land Between the Lakes last time. So lake is a great thing to take pictures of because there's like a little bit of motion.
Yeah.
Not so much that you basically get abstract art. So there's a little bit, you can see the clouds pop up and that kind of thing.
That makes me think that you could actually do that with an iPhone set to time lapse. That'll do it once every second on a time lapse.
Can you do it for 3 hours?
Oh, okay, you're doing it for the entire beginning to end there.
We're filling the entire the clip of the.
Okay, how many pictures was that going to be then? 5,000?
Yeah.
So I'd have to take a look at on a memory card for a DSLR. Exactly, you'd want to have a very big one. Then you're saying.
Yeah, it's basically fills up the thing.
Okay.
So yeah.
Word to the wise then, make sure, actually, I think, yes, for all of us, make sure you've got a clean memory card and you're ready to go with, you don't run out of memory halfway
All
through
your
the
batteries are charged, yes.
batteries. Also, I found it from last time's experience when I loved it. It went right over my parents' farm in East Tennessee. We just took the students down there and we set up in the pasture. But those cameras will get hot sitting out there for that many hours. Take some aluminum foil and just, wrap around a little part, not over the light meter or anything, but wrap over like that just to keep some of the sun off of them. And because the batteries also don't like getting real hot either. Another thing. We, last time we were able to see these. Has anybody heard of shadow bands? Okay, a few, okay. Get out and just take a white blanket, lay it out flat, and at just before totality begins or just after totality ends, look at it. You'll see you may see what looks like just sort of dark wavy patterns.
Yes.
They do not photograph well. We barely managed to catch video with an iPhone last time of it. We could see it pretty well, but we couldn't photograph it easily. But they're very ephemeral. This is it is thought to occur because at that point the sun is basically making a slit, even though it's curved.
Yeah.
That's coming through the atmosphere, and where you have your turbulence in the atmosphere, it's refracting in different ways. But we saw overlapping patterns moving in different directions, which would presumably be from different layers of the atmosphere as well.
So this is what we're calling wave bands or.
Shadow bands is the name. Shadow bands. Dave Turnshake, my old graduate advisor at Pitt, launched a balloon experiment to see if there was any evidence that some of these might even occur in the stratosphere. And he was using the balloon itself as the detector, as the screen, and then with an upward looking camera. Didn't see any evidence for them though. But that's something interesting, and it's I guess it's not always seen, and it's not very widely known. But just all you need is a white sheet, and you're ready to go.
That's good. I'm looking for a couple of like activities.
Yeah, that's a good public one, because I mean everybody without any training can look at the sheet.
And I have the eclipse, sorry, I have the solar viewer, you have the solar camera, the solar viewer, and so the kids can make a picture of the sun before it all gets started, and they can actually draw the sunspots on there.
Oh, in fact, that so with what you were saying there with the solar viewer, get yourself one of those 50-cent diffraction gratings on a slide. Put it over your camera, even maybe over the iPhone camera, and just before totality, or again just after, take a photo of the flash spectrum. And so again, you're going to have just that thin slit of the sun there, but now you're going to get the spectral lines coming out. And that looks really pretty neat, especially when you get the chromosphere showing, you get a lot of lines on it. I forgot to bring that dirt cheap little piece of plastic last time, and so I completely missed it. So I'm taking a pack of 100 this time, so I'll at least have one. Yeah, but that one, it's a neat look, and there are, wait, what was one other thing people have done? Certainly the time lapse. Shoot, I was trying to think of any other clever photography techniques. The one you're talking about, I think, is going to be the neatest one.
Oh, remember, Indy talking about the polarization, like how you can use your hands to.
On the part during partial.
Yeah, during partial where
Right.
it's slits.
So turn your fingers, separate your fingers a bit like that.
Yep.
And then as you turn them, you get sharp image versus not sharp image,
Yeah,
right?
blurry, yeah. Really? Yeah.
Because of the alignment of the crescent shape. So if they're aligned with the crescent shape versus perpendicular to it.
I just enjoy taking pictures of like when it goes to the trees. For example.
Yes.
Because that is-
Yeah, trees, colanders,
Yeah.
Straw hat,
straw hat, right?
I heard Ritz crackers. I haven't tried it.
The Ritz cracker technique,
Yeah.
okay.
There we go.
The pinhole, the Ritz cracker pinhole camera.
But-
Actually, you know what would be kind of funny? Would be to get a Ritz cracker, and you know how that you have your like eclipse viewers with a pinhole made out of a cereal box?
Yeah.
Cut a hole on side that there, tape white paper on the bottom side, and then put a pinhole on this side. You look through here and you got your pinhole. If you did that with the Ritz cracker for the pinhole in a Ritz cracker box, it'd be very self-referential and could be a nice little, public outreach there.
So our library has 3D printed template where you have like a little pinhole camera essentially. So you just have a little credit card size thing so that you can project onto something.
Uh-huh.
You just hold it. But yeah, they have 3D printed ones. Have like the library, the Louisville library, that kind of thing. So if you have access to a 3D printer and you give them a little bit of time, you can have handheld that people can use.
So that's nice. Oh, it was, but tell me again, you have the two parts to it?
No, it's
Just
just a
one?
little credit card with a hole in it. I mean, it's not.
Okay, so it's the pinhole rather than straight.
But if you can make a nice small hole with it.
Yeah, so if you've got an actual credit card or a business card or something as the screen, then or your hand, I guess.
Yeah.
That's nice, and a 3D printed pinhole camera.
Right, I thought that was,
Yeah. Yeah, Christine.
Yeah, right. You take a cup, like a solo cup, put like half-inch hole in it, and take a pair of reading glasses, take out the lenses, and tape the lens to it, and it makes it it's a nice projector, right? And it magnifies it a little bit.
Wait, now say that again. I was writing that.
Okay. So if you take what's called, you take reading glasses. take
Reading
one
glasses.
bottle of reading glasses, put it on a cup, like a plastic cup, whatever, with a small hole on the end. And then it magnifies the image.
Yeah, because your
of the
reading
sun.
glasses are convex lenses then.
Yeah.
Okay.
And it makes a nice
Okay,
Yeah, let's see. Oh, and yeah, the smaller the number, right, the bigger the image. So I have a 1.5 time lens that I can, it's basically like weight level. I just hold it out and that's where it's focused.
mm-hmm,
And I was trying it with, okay, that wouldn't work in here, but onto my dome around the edge. And you can see the details of the bulb and everything. It's great. Anyway. that's
but
okay.
thinking of polarization though, Joseph, you were mentioning polarization with, like large scale orientations. I'm assuming that the corona emits polarized light, but has anybody actually looked at that?
No.
Getting a Polaroid filter would be kind of interesting then during totality to just take two different directions on it and see what comes out.
Yeah. That's a good point. I never thought the corona would be polarized.
Well, it's very, very, I don't know, it's got magnetic fields. Doesn't everything with magnetic fields have something polarized?
That's the heating mechanism, right? But that is,
It's-
I mean, it's a big plasma that has a temperature of 1 million, 2 million Kelvin. That's where you see the X-rays. But it's,
No.
never thought about that it would be polarized.
Well, hold on a second. The camera's not, my phone's not
I
here.
would say it's space football up here. Right?
By the way, any of y'all online know if the corona emits polarized light?
I think it does, but I'm not a solar expert, but it's down near the base of the corona.
Okay.
There's some reflection of dust particles in the outer corona where they're not evaporated, and so it's a reflection, and any reflection has got to be polarized.
Okay. All right, well, I'll see if I can get a Polaroid filter from somewhere in the lab. I'm not actually sure if we have one. We should have a Polaroid filter sitting around in the physics lab. That seems stupid that we don't.
Is anyone going to be up high or like higher on the hill or something?
What are you thinking of?
Oh, this the, see the shadow.
Oh, yeah.
Oh, that's good. Well, if you're around mountains,
Well, but you're not exactly high up.
last time I was at 1,100 foot elevation, but I was surrounded by higher mountains. The neat thing was we saw the shadow move over to the other mountains in the time lapse.
Okay.
I had 3 cameras running. We had a Nikon Sport panoramic camera that we just mounted and kept it looking out towards the mountains and just let it run the whole time. We had a telephoto lens on another Nikon that was tracking the sun. And then we had a 85 millimeter lens that was just looking at the entire landscape. And we took, all of them were on intervalometers, so they just kept taking a picture every 30 seconds or something. But the neat thing was we could see in the time lapse on the panoramic, we could see that shadow move at what, 1,600 miles an hour, 2,000 miles an hour.
It's actually equal if you're on a flat surface. I remember not very well in Russia, but when I was in Gashi, we were on the fields and you could see the shadow actually coming.
Yeah. Also, what I didn't expect was, and I only found out later what it was, we saw a twilight kind of sunset red glow around it. It's the hydrogen alpha from the chromosphere. And because it's just a little bit broader than the moon.
Right.
And so you get around the edge of the moon's shadow, you get the chromosphere, you get the H alpha emission, and it looks like sunset colors, but it's not from scattering, it's from line emission.
That is cool.
That's a good thing. So that's the fun thing that I'll tell people that they can do with their phone is you can take a pano. And so the only picture I took last time was took a pano of the whole environment. So you actually see that red glow along the horizon, because how else can you show that easily, right? That there's essentially sunset around you.
Yeah.
Yes, yes.
That red glow is kind of neat.
Right, and it's easy to confuse because it looks like it's sunset because it's at the edge of the shadow, but it's not from the same cause. I'm trying to think if I have any. I've got an H alpha filter for the telescope, but I don't have anything really safe to hold that in to separate that.
So to say like take a pano, because that's sort of allows you to see the environment. All right.
Oh, I'm also gonna be doing, some citizen science projects during it, like one of the other things. Stuff. I mean, I found a couple online. Does anybody have getting good ones, good, easy ones to do with a group? I mean, I'm looking at using the, Globe Observer app, NASA is probably what I was gonna recommend. But
Mhm.
I don't know if anybody had any other ideas or knew of any other things.
Well, actually, one thing, and maybe not really citizen science, but
Yeah.
are we expected to have any stars, reasonably bright stars? Like last time we had Regulus.
Yeah.
And what about planets?
Orion,
Yeah.
4 planets, and the comet will be visible.
Okay, wait, hold on. Oh, wait, let me get a list of these here. So what was the first?
Yeah.
Uh,
I
Orion,
even be thinking on that, if it's.
The whole constellation Orion.
constellation Orion, easy to spot, and a bunch of planets. So I think 4 are visible, including Mars and Jupiter.
Yeah, and Saturn.
And there is a comet that might be,
Okay, do you remember the name or number of the comet?
not a clue.
Okay,
You know,
Um,
I saw a viewing guide, it was like, oh, there's gonna be a comet, like left of the sun. So,
Okay.
well,
well, actually, that's good because since Orion is right now
Yep.
just visible after sunset,
Right.
so it's gonna be moving on closer that to the sun there. That's gonna be neat.
It looks like Comet 12P,
That's it.
Pons Brooks.
What's the name after 12P?
Pons Brooks, so Pons Brooks.
Okay,
How bright is it supposed to be?
So not seeing that right off my, quick Google search here.
All right,
so.
that's fine.
oh, also another thing then, I was just thinking about trying to expose for the comet. But last time I didn't expose for it intentionally, but I caught it barely. On that, this time I'll try it on purpose. I caught the earth shine on the moon. I've actually got one photo where you can make out the seas and craters on the moon. Because when you've got that when you've got the solar eclipse, the earth is full.
Yes.
And so now, but you've got to expose it long enough. I think I might have gone just a little over 1 second was all. But if I got it a bit deeper and with a lower sensitivity setting so that you got less noise in there, but you could make out the seas, the Mario. You what?
Yeah.
I'm not gonna try to fuss too much with it.
Yeah, that's true.
Well, I've got it. It's going to be on an intervalometer so that I'm just going to set it and let it go.
Hopefully the weather's good.
Yeah, that's fingers crossed for that there. Also, one other thing, this is not really an eclipse thing, but just thinking what you can do with a cell phone now. I've been amazed to see it. I'll show as we're leaving. I'll show anybody who wants to see it. And the same amateur astronomer I've been working with showed me on Facebook that you can actually he's got an iPhone 12. I've got the 14 now. The nighttime sensitivity is good enough on those cameras. It can see Uranus with a handheld photo.
What?
Yeah. You go to the nighttime settings, you can get it to do a longer exposure. Handheld, it does alignment and stacking, even if you're kind of doing like this without too much. And Uranus comes out clearly.
No.
I've been doing it every week that there's a clear night, and since September, and I've been tracking Uranus and Jupiter as they went through retrograde motion and are starting back. And I've been putting it together, loaded up to astrometry.net, get a FITS file with a world coordinate system attached, put it up onto DS9, and then go through the time lapse on that now. And now you've got them co-aligned and do your time lapse that way.
Wow.
But I'll show that to you once we're offline. So anyway, neat stuff you can do with an iPhone now. And I think those galaxies and things like that are even better with nighttime photos. Okay, anybody else online with some helpful suggestions for the eclipse? And I see that we do have a whole lot of links that, Jerry, is that you who's put those up there? Okay, polarimetry papers, thanks. Are we able to get access to the links in the chat after we close?
You know where to save the chat, if you click on the.
We're gonna see about saving the chat links there, because I'd really like to take a look at those, but I'm not on my own computer here.
And then you can email it out.
Oh, that's very neat, thank you.
All right,
If
you can
click
do that,
on the
Dirk?
little menu, you see the little menu, button, the three dots on the bottom, down,
Yeah,
down, this one. Yep, big chat.
okay. So yeah, Dirk, are you able to take care of that?
I hope so. I mean, I have the recording, so I will stop the recording now.
Okay,
Thank you, everybody, and.
Bye, everybody.
Stop the meeting.
yep, we'll see you next year.